Okay, so the third talk in this session is called DisLog, a separation logic for disentanglement, and Alex Moine will be giving the talk. I knew I was going to forget that.
Okay, so hello everyone. My name is Alexandre Moine. I'm a PhD student at Inria, and I'm going to present joint work with Sam Westrick and Stephanie Balzer from Carnegie Mellon. And this work is about DisLog, a separation logic for disentanglement. So of course the question is, what is disentanglement? And in our case, we consider parallel programs. So disentanglement asserts that concurrently executing tasks remain oblivious to each other's allocations. Let me illustrate with a computation graph. So a computation graph consists of vertices, which represents a sequential unit of computations, or a task, and two outgoing edges are a fork, and two ingoing edges are a join. And let's say that this task right here allocate a location L. Well, to ensure disentanglement, this concurrently executing task is prevented from acquiring L. However, subsequent tasks, such as this one or this one, can safely acquire L. And as Stefan said, disentanglement is a property that broadly occurs. For example, pure programs are always disentangled because pure programs does not exchange allocations. And more generally, deterministically race-free programs are also disentangled. So it really broadly occurs, and again, as Stefan says, disentanglement guarantees a kind of locality, meaning that you can equip each task with its own local heap. And this is very useful. Indeed, thanks to this locality, disentanglement gives you fast memory management. Because each task has its own heap, it does not need to synchronize with other tasks for a garbage collection. And this is very well illustrated by the Maple MPL compiler for parallel ML developed at CMU. So it's a compiler for standard ML with a par primitive that heavily makes use of disentanglement to provide a fast memory management. But as it makes use of disentanglement, it has to ensure that the source program is indeed disentangled. And thanks to two recent line of works, MPL detects and even manages the entanglement at runtime. But we are at POPL', so the question is, of course, can we ensure statically that a program is disentangled? And this is exactly the contribution of this paper. We present the first program logic for disentanglement that is called DisLog, separation logic, with the notion of timestamps that I'm going to present. But we also present another separation logic called DisLog+, which is a standard separation logic for race-free programs, that is, separation logic without invariants. It yields disentanglement proof for free, since race-free programs are always disentangled. And we also provide extensions for binning for disentanglement races, which are write-write races and read-write races on pre-allocated data. But DisLog+ is not any separation logic. It works hand in hand with DisLog, meaning that the user can switch between the two logics during a proof and verify the easy parts, so the race-free parts using the standard DisLog+, and switch back to DisLog for the subtle racy parts of the program. And I will not spend time on this, but theory and examples are fully mechanized in Coq on top of the Iris framework. And this is also the roadmap of my talk. I will first present DisLog and then going back to DisLog+. So what are these timestamps? So we equip each task with a unique timestamp, t, and we said that a timestamp ti precedes a timestamp tj whenever there is a path from ti to tj in the computation graph. Then we define the disentanglement as follows. We say that if a location L prime points to L, and if ti dereferences L prime, that is, it acquires L from the heap, then L must have been allocated by a task preceding ti. So this is our definition of disentanglement. And our main idea to devise a separation logic for disentanglement is to reflect those timestamps within the logic. So we propose a new weakest precondition, WP, which is parameterized not only by E, the expression being verified, but by T, the current timestamp of the expression. So the timestamp at which the expression is being reduced. Moreover, the postcondition here is parameterized not only by V, the resulting value, but by T prime, the resulting timestamp of the evaluation. And then, for disentanglement, we introduce exactly the assertion that we need. That is the clock assertion, a new separation logic assertion that asserts that the location L was allocated by a task preceding T. So this is a new separation logic assertion, but it asserts knowledge and not ownership. Hence, it is what we call persistent, meaning that we can always duplicate a clock assertion. Then with this new WP and this clock assertion, we are ready to unveil our load rule, that is the core of the logic, that paraphrases the definition of disentanglement. Well, so the precondition is here, and it asserts that if L prime points to L, and if the task T dereferences L prime, that is, it acquires L from the heap, then L must have been allocated by a task preceding T. In the postcondition, we know that the resulting timestamp T prime is equal to T, since the load is sequential. The resulting value V is equal to L, and L prime still points to L. But we still lack a piece of the puzzle. How to reflect that time flies? How to express these dependencies between timestamps? Again, we introduce exactly the assertion that we need. So this is the precedence assertion. T precedes T prime in the underlying computation graph. Again, this is a persistent assertion, so we can duplicate precedence assertions. And two remarks about the persistent assertions. First, it forms a preorder. It is reflexive and transitive. Moreover, the clock assertion is monotonic with respect to the precedence preorder. A complex sentence to say that if L was allocated by a task preceding T, and if T precedes T prime, then L was allocated by a task preceding T prime. Now, let me show you how we generate these assertions during a proof. And thanks to their persistence, we can generate precedence and clock assertions at will. For example, this reasoning rule right here asserts that it's always safe to suppose that the resulting timestamp T prime is preceded by the current timestamp T in the post condition. Perhaps more interestingly, this rule witnesses that our logic prevents entanglement. Indeed, this rule asserts that if the location L is being manipulated by E, it occurs in the literal of E, then it is safe to suppose that L was allocated by a task preceding T, T being the current timestamp. Indeed, otherwise there would have been entanglement. However, our logic prevents entanglement, hence it is safe to generate clock assertion of locations of the current expression. And last but not least, the par rule, how to reason about a parallel pair inside our logic. So the parallel pair is E1, parallel E2 at current timestamp T, and we require, in the precondition, so we require the user to verify E1 at current timestamp T1. T1 being preceded by T, the current timestamp of the parallel pair. Then we also require the user to verify E2 at current timestamp T2, that is also preceded by T. But we universally quantify over T1 and T2, hence we prevent the user from comparing T1 and T2. In the post condition, we know that there exists a resulting timestamp T1 prime and a resulting value for V1 of E1, so satisfying the post condition psi1 of E1, and the same for E2. And we know that the resulting timestamp T1 prime precedes T prime, the resulting timestamp of the parallel pair itself, because T prime is a join point. And we know that the resulting location L points to the pair of the result of the evaluation of E1 and E2. Okay, enough of DisLog, and let's do a little interlude about races in separation logic, because you understood that determinacy races are particularly important for disentanglement. So recall the definition of a determinacy race. It asserts that the determinacy race consists of two concurrent atomic accesses to a location, and at least one is a right. Well, the key remark is that reasoning about races in separation logic is very subtle. Let me illustrate. you have two concurrent tasks that are going to write something inside a shared location, L, and a single points-to assertion, the ownership of the location. And well, you have to decide to which task you are going to give the points-to assertion. And of course, if you give it to the left task, you prevent verifying the right of the right task. And similarly, if you give the points-to the right task. And the solution to this is well known, is that you need invariance. You need to lose the ownership and just describe how the tasks are going to interact with the location. And the cool thing is that DisLog has invariance. So, for example, we can verify a subtle log-free hash set with races. But recall what I said in the beginning of this talk, race-free programs are always disentangled, meaning that a standard separation logic without timestamps, without clocks, without precedence, and without invariance guarantees disentanglement for free, since without invariance, we can only verify race-free programs, and race-free programs are disentangled. And DisLog Plus is such a separation logic. But it is encoded on top of DisLog, meaning that we get foundational proof of disentanglement for race-free programs, and we enable the user to freely switch between DisLog and DisLog Plus. How does it work? We call monotonicity to the rescue and define DisLog Plus assertions as monotonic predicates over a current timestamp. This is a very beautiful technique that we borrow from prior work on weak memory models, when DisLog manipulates monotonic view of the memory. But we manipulate monotonic predicates over current timestamp. And the key idea of DisLog Plus is to define a points-to assertion that guarantees disentanglement. So we define the points-to assertion of DisLog Plus as the points-to assertion of DisLog and the knowledge that the value being pointed by was allocated before t bearing the current timestamp. And notice that since the points-to assertion of DisLog Plus is parameterized by the current timestamp that will change over time, it cannot occur inside an invariant, since invariant cannot change over time. And I want to insist that DisLog Plus is a standard separation logic. So we have a weakest precondition, WPM, a monotonic WP that is defined in terms of WP of DisLog. And for example, we have the standard load rule of separation logic, since the clock assertion is bundled inside the points-to assertion of DisLog Plus. Then, thanks to monotonicity, we even have a standard power rule that holds. So DisLog Plus is a standard separation logic. But as I said, we can convert between DisLog and DisLog Plus. So verifying a WPM in DisLog Plus is equivalent to verifying a WP in DisLog. And this is very useful, since it asserts that we can verify a DisLog Plus interface using DisLog, and conversely, during a DisLog proof, you can use a DisLog Plus specification, thanks to this conversion theorem. I do not have the time to cover everything, so read the paper for details. We present extensions to DisLog Plus for bending races with atomic reads and writes. So we provide write-only points-to assertions for write-write races, and a set of objectivity lemmas for reasoning on races on pre-allocated data. We present the soundness proof and the mechanization, and we cover several case studies, so spin lock, parallel lookup in a lazy collection, and 2 implementation of a log-free hash set. So read the paper. And in conclusion, I just presented DisLog, the first program logic for disentanglement, and DisLog Plus, a high-level program logic for race-free programs. The mechanization is freely available here. And as future work, we would like to devise a type system, proof sound with semantic typing and DisLog. And the talk just before introduced added futures to disentanglement. So of course the question is how to adapt DisLog to these futures. Thank you for your attention, and I will be on the postdoc market next fall.
Questions? Okay, well, while we're going, I'll ask the Discord question. So can we understand the dynamic mechanisms to detect, repair, entanglement through your work? Would adding them to your system add invariance back into DisLog Plus?
Sorry, can you repeat?
Sorry. So can you understand the work on dynamic mechanisms
Yeah.
to detect and repair entanglement
Yeah.
through the lens of your work? And would adding these dynamic mechanisms to your system add invariance back to DisLog?
Yes, so I think you can, with this mechanism, generate clock assertions and precedence within the DisLog logic, and it will show up in the DisLog plus logic.
Yeah, so you mentioned that the two-level logic approach is inspired by weak memory. Is there any chance you could integrate weak memory into this?
I don't know at all.
All right.
But yeah, perhaps.
Thank you. Part of what you have presented reminded me very much of ownership types, and ownership types as were proposed by Jan Vitek and James Noble in the 90s, where you have got regions and objects in one region can be pointing to objects in the regions above, but not the other way around. And that all of it can be enforced through a type system. And Stephanie knows that work very well.
Okay.
So, but it seemed to me you presented it through separation logic, and I was wondering, do you need the full power of separation logic? Can it not just be a type system?
Yes.
And some of it, then you, like you have two logics now, you can have a type system and two logics.
Yes, so I definitely have to look into ownership types, but do they prevent races? Because disentanglement allow races. It's a generalization of races. So to verify all disentangled program, you need something more.
You can use ownership types
to verify races?
I think we should take it offline,
Yeah.
but you can use ownership types to prevent races. But of course, if you want to be more fine-grained, ownership types are not enough. But you have got the stronger logic for that.
Yeah.
But in order to enforce this topology, it seems to me
Yes, I think
you
it
are
will
just
work.
using types.
Yeah.
Any other questions? So I guess we should just thank the speaker again.